Everyone, thank you so much for watching this presentation. My name is Sebastián Montoya. I'm a PhD student in the Civil and Environmental Engineering Department at the University of Maine, working with professors Aaron Gallant and Bill Davids. Our research relates to the structural testing of micropile thread connections. So in the case of steel casing micropiles, what we have it's an installation process that is typically, as shown in the diagram, where we start drilling the pipe that is relatively small diameter, less than 12 inches. So it's drilled into the soil, and you start with a single segment, but as you are going deeper and deeper, you start connecting several of the segments, so you have multiple segments to reach your desired depth. The connection for those segments are threads connection. So when you reach your desired depth, you remove your drill bit and have the opportunity to place a reinforcing bar and to fill the crowd. This construction method provides several advantages. First of all, it develops high geotechnical capacity with tension and compression that rely on essentially on the friction with the casing. They are suitable for challenging subsurface conditions like shallow bedrocks, where you can develop a rock socket, thing you can do while you're drilling piles. Are suitable site with limited access. That's because require relatively small equipment. And this segmental installation, I really want to point out that it's especially advantageous in a situation where you have a low clearance. But despite their capacity, intention, and compression, they show relatively small capacity bending. And the reason for that is that the thread connection is the Achilles heel of the micro. Typical thread connection looks like the diagram we have in the left, where we have triangular threads and a taper wall, and essentially a pin box connection. So you just have to thread one end into the other. And consequence of the geometry and the thread detail you have is that you can present two failure modes, as I'm showing for the figures in the right. So as seen here, one of the failure modes, it's called jump out in the upper right. What happens there is that the threads ride one over the other, not losing contact in between them. And as a consequence, you can transfer any further bending moment. Or another thing that can happen to you is that you develop a crack in your connection because you have a reduction in section, very likely you have stress concentrations, imperfections, so you develop a crack, that crack propagates and it ends disconnecting two pieces of the micropile. It's consequently no bending capacity. But how weak is weak? When we say that the connection is weak, well, let's say that in terms of how weak it is compared with a micropile that doesn't have joints. What if our micropile were continuous? So that's what I'm showing in the diagram here, where I compiled about 40 4-point bending test report in the literature. In the vertical axis is showing the joint capacity, MU, the bending moment that causes failure at the joint, and is normalized by the yielding moment of a continuous pile. So a ratio of 1, MU or MY equal 1 means that the joint fails at the same load as a continuous pile will do, or a ratio less than 1 will means that the joint fails at a lower moment than a continuous pile will do. And a bigger than 1 means that the micropile will fail first at the continuous section rather than at the joint. In the horizontal axis, I'm presenting you these ratios for different casing diameters in inches. So what we observe is that we go from the smaller as we go from smaller to bigger diameters, this ratio reducing. So it means that the bigger it gets our pile, the less we can expect our joint to take full advantage of the capacity of the pile. And what I'm showing additional to that is a red line that it's the estimation based on the FHWA manual provisions for all these different diameters. So you observe, regardless of the diameter and regardless of the thread details, and the length of the connection, or the material that I'm using, I have a 50% reduction. So I can expect my joint to be about 1/2 of the capacity of the intact section. While we observed that most of the tests, most of the specimens we found in the literature have ratios well above 0.5, very few of them are below that, which means we need a more accurate way to predict that capacity at the joint, especially considering for the thread details, which is not available at the moment. Also, the tests that report there do not include a reinforcing bar. Very few tests have been done. Very few work has been done on specimens including reinforcing bars. None of them includes combined loading. Right now in the literature, you can't find anything about the joint capacity, including bending and axial loads. And in general, there's a lack of understanding as there's really no accepted methodology for estimating the capacity of the joint. So that's why at UMaine we propose to carry a testing program. Our piles look like this right now. We already went through the process of threading together the pieces, trying to reflect the conditions of installation on field. We fill them with grout, and some of them with installed rebars. We will going to do 63 different tests, essentially grouping them in 20, where we have different thread details, thread shapes, thread lengths, different pipe diameters, different wall thickness, and so that we can capture the behavior of these threads for a wide range of conditions. Also, we are going to include reinforcing bar, as I told you, and in some of the cases, we're going to apply compressive loads. So how are we going to do this? This is an schematic representation of what our testing will looks like. We will have a 4-point bending test performing a micropile specimen. So the micropile is resting horizontally on bearing blocks. We're going to use 2-point loads so that we have a constant bending moment in the middle span. And right at the middle of our specimen, there's a thread joint at which we will get focus. We are going to monitor displacements and rotations through the length of the pile, but we are going to pay more attention at the location of the joint, where we are going to use digital image correlation to have a detailed field of strains and displacements. Also, the combined loading, if just in case you wonder, we are going to do simultaneous compression and bending by using a post-tensioning system and an unbound Dewey Dack bar inside the element. So we first apply the compression through the Dewey Dack bar, and then we apply the lateral loads. But what are we going to do with all this data? Well, what we want to do is to develop an analytical model for predicting the bending capacity of the joint. Conceptually, our model looks like this. It's 2 pipes, one embedded inside the other. They are represented the pin and box ends of the connections. Those pipes vary in thickness so that we can represent the taper of the threads, and they will be interacting. So we are not representing the thread geometry, and we are not solving a contact problem. We will be representing the interaction in between the threads by constraining the way in which these pipes can deform one relative to the other. So we can have the radial displacements U and the longitudinal displacements W that happen in each of these pipes. We can compute hoop strains, which is E theta. We can compute axial strains, that's E zeta. And we can compute our shear strain, which is gamma. So we have a suitable constitutive model. We can, based on these strains, compute our stresses, and with the stresses, we can integrate to obtain the moments. The big question is, what are the displacements in a thread connection? Because of the discontinuity presented by the threads, the formation of this embedding uh, does no longer follow the Euler-Bernoulli assumption of plane section remain plane. So we have to come up with a suitable functions that can tell you the distribution of this displacement over the cross section. That's where the DAC will play a big role. It's gonna provide us a detailed description of how the pipe is deforming on every position, and with that we can fit functions. We are going to find the most suitable functions to represent these displacements, and we are going to parameterize that in terms of the parameters that we know. That is the geometry of the threads, the diameter of our pipe, and the thickness of our wall. Stay in touch. Do not hesitate to reach out if you have questions. And if you're interested in this project, definitely shoot me an email. I'll keep you posted with the results of the test. Thank you so much.